The first thing we discussed in this chapter was about the electric charges, the entity which enables the attraction or repulsion between two bodies, and that is observed that these electrical identities are called as charges. They had got some certain properties like the like charges repel each other and unlike charges attract each other, the basic first property. Second, the charges are additive in nature, means the total charge on a system can be obtained by simply adding the various charges present in the system. Thirdly, charges are quantized. It's an important expression. It had that Q equals to plus minus n into E. That is where n is the number of electrons or holes being transferred and E is the charge of each electron. Plus and minus, the charge on a body can be positive as well as negative. It establishes that this fact that charge cannot be in fraction, like mass. Mass is able to have fractional values, but the charges do not have the fractional values. This is in concern to the concept that the charges are because of the transfer of electrons, and the electrons cannot be transferred in fractions. They will be transferred in whole numbers. So that is why the charges are considered to be quantized. And fourth, the important one, that the charges are always conserved. The total charge present on a system can neither be increased nor be decreased, means can neither be created nor be destroyed. It remains conserved. Now, moving further, we had got the discussion about the Coulombs Law. Coulombs Law says that the force between two charges, they can attract or repel depending upon their nature, but the force will be there, and this force was identified to be proportional to product of their magnitudes and the square inversely proportional to square of the distance between the two charges. F proportional to Q1 Q2 upon R square. When we observe this and we identify this proportionality replaced with equality, so a constant small k, that is 1 upon 4 pi epsilon naught was introduced here. This epsilon naught was termed as absolute permittivity, which had a value, epsilon naught had a value of 8.85 10 to the power minus 12 Coulomb square Newton meter minus 2. This is the value of epsilon naught. However, the value of this complete was identified to be 9 into 10 to the power 9 Newton meter per Coulomb square. This is the value of 1 upon 4 pi epsilon naught, 9 into 10 to the power 9. This value we had got it. Now we introduce another term, dielectrics, a kind of insulators which help in the transfer of charge without following the rules of conduction. So what they do, that is called as induction. They use the concept of induction, we will discuss here. But dielectric constant was defined in terms of force between two charges like this, that K equals to Fo upon Fm. Fo means the force between two charges in air or vacuum ratio the force between same two charges at the same distance in the given medium. So this K will be the dielectric constant of that medium. Okay, so K is that medium in which the charges were replaced. Here they were placed, not replaced, they were placed, they were placed. So this is K, dielectric constant. Now we discuss various methods of charging. The various methods of charging include conduction, induction and friction. Already we have discussed that the charges are obtained by the transfer of electrons. So electrons are transferred when we are basically studying about the concept of friction. Frictional electricity is the main chapter here. Frictional electricity means we rub the two bodies and the charges are being transferred from one body to another because of the friction created between the two bodies. Now, frictional electricity, friction. After that, once a body is charged, then there are two more methods of charging the other uncharged body, conduction and induction. Body A is charged, we bring the body B and keep it in touch with body A. So body B will acquire some charge. That charge will be of same nature. If body A is positive, body B will also acquire a positive charge. If body A is negative, body B will also acquire a negative charge. Also, if bodies are identical, means they have got the same material, same size, then the charge will get distributed evenly. Means if charge on A is Q and B is identical to A, then after touching, A and B will acquire the same charge, Q by 2 and Q by 2 on each other. But in case of induction, what happens? First thing, the physical contact is not required. A body charge is held in the neighborhood of an uncharged body, and this induces the charge on the other body. So in this, the physical contact between the two bodies is not there like in conduction. Secondly, conduction has got the development of like charge, but in induction the charges developed are unlike. Means if one was positive, then the other body will acquire a negative charge. Then after that we got the concept of electric field intensity. Electric field, the space or region around a given charge within which it can attract or repel any other charge. Field intensity means the force on the given charge that is of unit value, or simply force per unit charge, is known as the electric field intensity at a given point due to a given charge. From this we can also conclude that force is equal to Q0 into E. This gives us the physical significance, that the physical significance of electric field is this. Knowledge of electric field at a point helps us in determining the force in magnitude as well as in direction on a charge placed at that particular point. I repeat, the electric field intensity at a given point helps in determining the magnitude as well as direction of a force on a given charge held at that point. So this is the physical significance of the concept of electric field. 1 mark important question. Then electric field lines, these are the paths on which if we draw a tangent, then they show the direction of the electric field at a particular point. We observed their properties and we could find out the most important one, that the lines never intersect each other, because if they intersect, there will be two directions at the same point, which is not possible. So this is the concept of electric field lines. Other properties are with you can go through them. After that we had the concept of electric dipole in this chapter. Dipole is comprised of two charges minus Q and plus Q separated by a small distance 2a. So this is electric dipole, two equal unlike charges separated by a certain distance, small distance. Then electric dipole has got dipole moment, which is termed as the strength of the electric dipole, and that is obtained to be equal to either charge with multiplied to the distance between the two charges. Distance between two charges is taken as dipole length, so P equals to Q into 2a, either charge multiplied to dipole length. We observe that we have put here a vector sign. It shows that dipole moment is a vector quantity. So yes, dipole moment is a vector quantity which is always directed from minus Q to plus Q. Remember, dipole moment is a vector quantity which is always directed from minus Q to plus Q. Then dipole fields, the dipole is there, so it will have its own electric field. 2 points are there, axial and equatorial. Axial along the axis of dipole and equatorial perpendicular bisector of axis. So axial point per the field, this is given as 2 kpr upon r square minus a square to power 2, where k is 1 upon 4 pi epsilon naught, p is the dipole moment, r is the distance of point of observation from the center of the dipole. R is distance of point of observation from the center of dipole. So this is the expression for axial field. However, if the point shifts to its equatorial point, equatorial line, then E equatorial is kp upon r square plus a square to power 3 by 2. Same concept. For a short dipole, if the dipole has a very small length, as small as possible, then the E axial will be twice of E equatorial. Remember this. The axial field will be twice that of equatorial field in case of a short dipole. Then dipole, when placed in a uniform electric field, experiences a torque that tends to rotate it, and that torque is given as Pe sin theta. Here we have got two conditions, whether theta is 0 or theta is 180. In both conditions, torque comes out to be 0. This is equilibrium, but this is the condition for stable equilibrium and this is the condition for unstable equilibrium. Clear that we had discussed. So this is torque on dipole. It is stable equilibrium and this is unstable equilibrium. Remember this thing. Clear? So this is the torque on a dipole. Then the Gauss's law we had. Gauss's law says that the electric flux through a given surface is 1 upon epsilon naught times the charge enclosed by the surface. And we could find it out that here the charge must be enclosed by the surface for which the flux is to be counted. If we are finding the flux of this surface where the charge is outside the surface, so for this charge, this surface will have no flux. The charge must be enclosed by the surface. Then only we can obtain the flux for that given surface. And before finding the flux, we have to identify the net charge enclosed by the surface. If say within the surface we have a charge of plus 5, minus 3, plus 2. So net charge will come out to be 5 minus 3 plus 2, that is 4. Accordingly, we will identify the flux. So remember this thing, if this is the net charge upon epsilon naught. Now we applied the Gauss's law for identifying the field due to an infinitely long charged wire, uniformly charged wire, and E was found to be lambda upon 2 pi epsilon naught r, where lambda is taken to be the line charge density, means charge per unit length for uniform charge distribution. Similarly, for an infinite plane sheet of charge, if a sheet we are obtaining for a plane sheet, for that we had got that E equals to sigma upon 2 epsilon naught, where sigma is the surface charge density, charge per unit area. And lastly, for a spherical shell, though we can assume the spherical shell to be like a point charge, and then this shell will have the same field as because of point charge, that is kq upon r square. But for a spherical shell, we can also obtain the relation sigma r square upon epsilon naught small r square, where capital R shows the radius of the shell and small r shows the distance of the point from the center of the shell. Here, remember one thing, that for this shell, inside the shell there will be no field because the charge on the shell resides on the outer surface. So interior surface will enclose no charge and hence no electric field. Remember this thing. So this is all about the chapter 1. A concise summary of this chapter. You must revise it properly. A few numericals from this chapter just to give an idea how you can do this. Some questions. First is, we have been given 2 point charges plus 12E and plus 3E separated by a distance 20 centimeter. We have to find the point at which the net field is 0. The field because of these two charges is 0. So remember, we have discussed earlier as well, if for like charges, the point where the net field or the net force is 0 lies between the two charges on the line joining them, first thing. And secondly, it will be closer to the smaller charge. It will be closer to the smaller charge. So this neutral point C we have taken is closer to smaller charge plus 3E. But because we have to find a distance from plus 2E, bigger charge, plus 12E, so this distance we have taken as x. So from 3E it remains 20 minus x. AC is x, BC is 20 minus x. Now as the net field is 0, it means the field of A equals to the field of B. Directions will be opposite. So the net field comes out to be 0. Formula is kq upon r square. So k into 12e upon x square equals to k into 3e upon 20 minus x square. Solving it out, we get that x comes out to be 40 by 3 centimeter, and this is a distance from plus 12e charge. Now proceeding further to the next numerical, we have got two large metal plates, each of area 1 meter square, placed at 5 centimeter. They have been kept at distance 5 centimeter facing each other, and they carry equal and opposite charges. Means the plates are having equal and opposite charges. The field between the plates is 1000 Newton per Coulomb. Find the charges. Now as the charges are equal and opposite, we know that the net field between the two plates is sigma 1 minus sigma 2 upon 2 epsilon naught. This is an outcome of electric field concept by Gauss's theorem, by using Gauss's theorem. But as the charges are equal and opposite, so net field comes out to be this, that also we had discussed in the chapter. Now sigma is surface charge density, that is Q by A. So E comes out to be Q upon epsilon naught A. We have to find Q, replace this, find the values, and the charge comes out to be 8.85 into 10 to the power minus 9 coulomb. Simple, very easy. That the plates are being given. Sometimes it can be given that the plates and the charges are given, and you have to find the field between them. Do the same pattern. Sigma will be Q upon A. Put the values of Q, epsilon naught A and you will get the answer. Same pattern. Now, another numerical we have got, that in this system, we have got a charge at point A where x is 0, the charge at point B where x is 50 centimeter, and the charge at point C where x is 120 centimeter. We have to find the net force at point where we have kept minus 4 microcoulomb charge. See, minus 4 microcoulomb charge we are placing here. This is between this and this. So point A will have an attractive force on this, force due to A. And point C will have repulsive force on this, force due to C. Why? It is positive, negative attraction, negative, negative repulsion. So both the fields or the forces are in left direction. So net force will be simply the sum of the two forces. The force due to A plus force due to C. KQA QB upon distance of AB square, KQB QC upon distance of BC square. AB distance is 50 centimeter, means 0.5 meter. Distance of BC, positions are 0, 50, 120. So this will be 70 centimeter. Distance between B and C will be 70 centimeter, means 0.7 meter. So place the values in this expression of QA, QB and distance square, QB, QC and distance of, this is to be, yes, QB, QC and distance of BC is square. We put this, we solve it, the answer comes out to be 0.799 Newton. C, this will be acting towards left. So direction and value can be identified by this. So these three numericals, just a glimpse. Using these, just an idea, using these you can discuss or you can find out various numericals. Try them.